All right. So let's go ahead and finish off chapter 18 here. We introduced a bunch of different functional groups, so we got to do some nomenclature. All right, so we're going to start with epoxides here, and we're going to name this simple 3-carbon epoxide. And we have our same 4 steps as always here. What we want to note about epoxide nomenclature is that epoxides are treated as substituents. Right, so as opposed to functional groups in our nomenclature, these things go out front of the name. They don't have anything special like priority associated with them. It's just all about having the lowest possible number in the name. Okay, so first step 1 is to find our parent chain. And then step 2 is to identify our substituents. Again, our epoxide is going to be considered a substituent, and we call it an epoxy group. Okay, so for substituents, epoxides are epoxy groups. We're going to number our parent chains so that we have the lowest number in the name. So I'm going to number from right to left here. All right. And then when we go to assemble the name, and this is the weirdest part about epoxides, you're going to include both locants in your name, meaning the numbers of both carbons that that epoxide is attached to. So this is 1,2 epoxy propane. And I'm sure they did this because there's some special case scenario where the 2 carbons aren't directly next to each other. Like a 1,5, or I don't even know. It'd be some really weird special case scenario here. But nonetheless, we're going to include both of the locants in our name for an epoxy group. All right, and truthfully, there is another nomenclature scheme for epoxies out there, or epoxides out there, but this is the one in our textbook, so this is the one we're going to stick with here. It's also a little bit simpler, so I'm cool with that. All right. So again, our epoxy group is a substituent. It's out front of the name here. So our parent chain is just the propane. Nothing fancy on the back end of the name there. Just the ANE for the alkane. Okay, and we're going to keep it pretty simple with epoxide nomenclature here. That's about as complicated as it gets. So everybody take a second and name these 2 epoxides for me. Okay, so my parent chain here are these 1, 2, 3, 4, 5 carbons. I have my epoxy group here. And I'm going to number my parent chain in such a way that puts that epoxy group at the lowest possible number. So this would be 2, 3 epoxy pentane. All right, again, we include both locants in the name for our epoxy groups. All right, same thing over here. Find my parent chain. 1, 2, 3, 4, 5, 6, 7 carbons. I'm going to number these both ways here. 1, 2, 3, 4, 5, 6, 7. We're going the other way. 1, 2, 3, 4, 5, 6, 7. Right, which one of these numbering schemes am I going to pick? Red or the blue? So it's going to be the blue because these epoxy groups have nothing special with them, right? I'm just going to list all my numbers here. This blue would be a 2, a 4, and a 5. Red would be a 3, a 4, and a 6. So blue loses. It's going to, or I'm sorry, so red loses. It's going to be that blue numbering scheme. All right, again, these don't have priority, they are just substituents. So then putting it all together, I need to assemble my name in alphabetical order, A, B, C, D, E, F. All right, so 4, 5, epoxy, 2, fluoroheptane. Okay, so again, epoxies, nothing really special about them as far as functional groups go. They're treated as substituents in our nomenclature scheme. We refer to them as epoxy groups. The weirdest thing about them is that you're going to include both the locants of both carbons that they're attached to in the name.
Question.
Yeah.
There would never be a double bond. Like, how would we name it if there was a double bond?
Then it would be a heftene.
Just change the
Yeah, you would just change the back end, right? So you would put like, if we want to just go ahead and do that, like put a double bond right here, then that would be 4, 5 epoxy, 2 fluoro, 1 heptene. You have to include the locant of the double bond, just like always, right? But yes, that part goes in the back half of this name. So like the epoxy group is like a methyl group or a fluoro group. It always just goes out front. Okay, so for sulfides, we're only going to stick to the common name scheme for naming our sulfides. Okay, of course there is an IUPAC naming scheme, but honestly you just really don't encounter very many sulfides out there in the wild. I managed to go my entire chemistry career without ever knowing what the real IUPAC name was for these here, so the common name is what is usually used to refer to them, kind of just like ethers, right? So ethers are also most commonly referred to by their common names. And sulfides are analogous to ethers, but with a sulfur in place of our oxygen. And our common name scheme for these are just like we saw for ethers, right? There's necessarily an alkyl group on either side of that sulfur. So you're going to, step 1, name those 2 alkyl groups. On this side here, I have a 2-carbon alkyl group, what we would call an ethyl group. And on the other side, I have a 1-carbon alkyl group, what we would call a methyl group. Okay, and then we're going to assemble in alphabetical order. Followed by the word sulfide. so I'm going to put these two alkyl groups in alphabetical order. So this one would be ethyl, methyl, sulfide. So let's name these two sulfides down here according to this common name scheme. Yeah, I don't. Is anybody going to be opposed to me killing this thing? Sorry, buddy. Wrong place. Is that the same one? Yeah. Oh my god. I thought I got it. Alright. If he comes back, it's not the same one. All right, so I'm going to look on this side. I have a 1, 2, 3 carbon group, so a propyl group. If I look on the other side, I also have a 3 carbon group, another propyl group. So how am I going to build this into my name? Dipropyl sulfide. Okay. Alright, so let's do the right half first, because this is the easy one. We have a methyl group over on this side. Alright? For this one here, these are one of these branched alkyl groups. What prefix do we use when there's a fork at the end? Iso, okay? And so I wanted to do this example just to stress that when we use our common names, the meth, the eth, the prop, the number of carbons designation refers to the total number of carbons that are in that group. So this is an iso group, and it's an iso 1, 2, 3, 4, 5, 6, an isohexyl group. Those common names, the total number of carbons that are in that group. So this would be isohexyl methyl sulfide. So for our sulfides, we're just going to stick to the common name scheme, and it's very similar to ethers, just with sulfide in place of ether. You look on either side, you name your alkyl groups, you put them in alphabetical order, followed by the word sulfide. All right, where we're going to complicate things here is our thiol nomenclature. Okay, and by complicate things here, y'all have learned just about every rule there is to organic chemistry nomenclature, except for one big one here, and that's what we're going to use this thiol nomenclature to introduce. All right, so that's going to come with when we have multiple functional groups in a molecule. We're not going to do that quite yet. All right, so step one, just naming normal old thiols. Okay. So we have to find our parent chain, and I'm going to put an alcohol and a thiol right next to each other so we can see the similarity between these two groups. Okay, we know that alcohols, we use what suffix for? All. So if we were to name this alcohol right here, this would be what? Everybody take a second and name this alcohol. Yeah, and not just propanol, but 1-propanol. We got to include the locant. 1-propanol, right? Because there is such a thing as 2-propanol, so we have to make sure to include that locant. All right, we're going to see something very similar for thiols, except for the suffix that we use is thiol. Functional group name and the suffix are the same. Okay, so when we put this together here, I'm going to replace the OL with the thiol, 1-prop-N thiol. All right, but there's this one problem that we are always trying to avoid in our organic chemistry nomenclature, which is putting two consonants next to one another. So we're not going to put those two consonants next to one another. We're going to retain the E on the end of that. So it's actually propane thiol. All right, so for thiols, because they start with the consonant, we're going to retain the E. Okay, they are not treated as substituents. All right, we can note that they are functional groups. They do have priority. Okay, I am going to leave some space here because, like I said, I'm going to complicate things. So I'm going to sort of introduce some new rules under substituent and numbering here in a second. But maybe we should put at the very top here, thiols are functional groups with priority. Okay, so you're going to name them very similar to alcohols, just with the suffix thiol, but because that suffix starts with a consonant, you're going to keep the E on the end as well. All right, so let's just do 2 thiols and then we'll complicate things. so I'm going to find my parent chain, these 1, 2, 3, 4 carbons. I'm going to number my parent chain to give that thiol group the lowest possible number. And when I put it together, 2-butane thiol. I'm going to retain, thiol. I'm going to retain the E on the end of that alkyl chain. Okay, so here again, we're going to find our parent chain. 1, 2, 3, 4, 5, 6. We're going to number our parent chain. We'll go from left to right, and then from right to left. And which one of these two numbering schemes is correct? The red, because I'm going to prioritize that thiol group, right? It's one of those functional groups that have priority, and so I'm not going to look at where that chloro group is at all. I'm just going to make sure that thiol group has the lowest possible number. So this would be 5-chloro, 3-hexane thiol. Okay, so the complication, the last little twist we're going to throw in here, is if we have a molecule that has two functional groups in it, both of which have priority. So for example, if we have both an alcohol group and a thiol group in the same molecule, how do we go about naming something like this? Okay, there are two functional groups in here. We know alcohol groups have priority. We know thiol groups have priority. So what's the deal? How do we deal with something like this? All right, so in the world of organic chemistry, every functional group is assigned a priority, and they're all a ranking. It's a hierarchy, right? So there's some functional, I don't even remember what it is, maybe a carboxylic acid that has the highest priority, and then they're all ranked from there, okay? So you go Wikipedia, organic functional group priorities, and you see this big giant master list that comes up. So this is a subset of that list. Okay? Alcohols are the functional group that at this point in our course have the highest priority. Okay? We've talked about amines. We haven't talked about the nomenclature, but just to leave it up here so that we have an example. And then we have our thiols. Both of these are lower priority groups than an alcohol group. All right? So, first thing, when we number our parent chain, we're only going to pay attention to the location of that highest priority group. Right? The highest priority one wins. Okay? So, when we number our parent chain, our numbering is going to be determined only by the highest priority group. So in my numbering of this molecule here, I'm going to make sure that alcohol group has the lowest priority. I don't care about the thiol group when it comes to the numbering, right? It loses all of its importance because of the presence of that alcohol group. All right, now the other twist, the big twist, is the fact that each of these functional groups, not only do they have the suffix, which we learned about, all for alcohols, thiol for thiols. We haven't talked about it, but amines are amine. They have these suffixes that we use to refer to them, but they also have these prefixes associated with them. All right? So when we have a molecule that has two different functional groups in there, the highest priority group you refer to by its suffix, but the lower priority group you no longer refer to by its suffix, you refer to it by its prefix. It becomes just another substituent. Okay, so we can kind of save amine. I just wanted to sort of show a few different functional groups. We'll save amines for when we get there. All right, but if we have a molecule that has both an alcohol group and a thiol group in there, we're going to refer to the position of the alcohol group using the suffix -ol, but the thiol group is no longer a thiol. It becomes a mercapto group. You refer to it by its prefix. It's now a substituent on that parent chain. Okay? And pretty soon we'll learn about groups that are more important than alcohols, and we'll start referring to alcohols by their suffix or by their prefix hydroxy. All right? But for our substituents, the lower priority group becomes a substituent. And again, for our thiols, that substituent name is no longer thiol, it's mercapto. I don't know who came up with it. All of the other ones kind of make sense. This one's a little bit out of left field here. Okay? So when I'm looking at this molecule here, not only am I going to number, paying attention to where my alcohol group is, ignoring that thiol group altogether, I'm also going to consider this a substituent with the name mercapto. So when I put this together here, this molecule is 4-mercapto 2-pentanol. My thiol group is no longer special. It's now just another substituent that goes out front. And the higher priority functional group is the one that gets the special position, the suffix position in the back half of the name. All right, so let's do 2 more examples here. I'm going to find my parent chain. 1, 2, 3, 4, 5 carbons. I'm going to number my parent chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And which one of these numbering schemes am I going to pick, red or blue? Blue, because my thiol group is no longer special. It is just another substituent, what we would refer to as a mercapto group. Okay, so when I put my name together here, or when I put my numbering down, the only thing I care about is the position of that highest priority alcohol group. So this would be 5 mercapto, 2 pentanol. Okay, same thing here. I'm going to find my parent chain. 1, 2, 3, 4, 5. I'm going to number my parent chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I'm only going to pay attention to my alcohol group, but regardless of which one I pick, my alcohol group is at carbon 3. Okay, so let's take a poll real quick. Who thinks that we should pick the blue numbering scheme? And what about the red numbering scheme? Okay, so it's a tie. So now I'm going to look to my other substituents to break my tie. This is a mercapto group. This is a chloro group. Okay? Regardless of whether I pick the blue or the red numbering scheme, I'm going to have 2, 3, 4 in the name. Right? We want the lowest possible number, but I got a tie when I start numbering stuff. So how do we break our ties? Alphabetical order. And chloro comes before mercapto. Again, there is no longer anything special about that SH because of the presence of that higher priority alcohol group in the name. It's not like we're going to look to it second or anything like that. It just loses all of its privilege. Okay? So absolutely, we're going to pick the blue numbering scheme because chloro beats mercapto in alphabetical order. So this will be 2 chloro, 4 mercapto, 3 pentanol. All right, so as far as what you can expect to have on your exam, I'm going to give you a version of this chart on your exam here, okay? I will tell you the ranking of the priorities. I don't really find it necessary to be memorizing what's higher priority than what, okay? What I am going to redact from this chart here, when I put it on your constants page, is the suffix name. You have to know what the suffix of an alcohol is and what the suffix of a thiol is. What I will give you is the prefix name. So I will give you the mercapto, I will give you the hydro. We're going to just continue to build onto this list as we introduce more and more functional groups. We'll introduce an amine group here. And again, I'm going to give you that amino prefix. I'm going to take away the suffix. All right, so the suffixes we should know. That's how we refer to those molecules when that functional group's all by themselves. When we have mixed functional groups, we have to pay attention to our priority list, and this is like a version of what I would give you on a priority list here, okay? All right. So, last thing to cover, and then we're gonna review some alcohol reactions, is something that we talked a little bit, started talking about last time, but it's a little more nuanced than what we were able to cover last class, and that is the stereochemistry of these epoxide reactions. All right, so let's just do a review of the type that we did cover here, and that was when we have rings. All right, so I'm going to do a slightly different example. Okay, so the first thing we're going to do is take our ring and treat it with bromine in the presence of water, followed by NaOH. And then we're going to take that and we're going to add in a nucleophile. Let's go ahead and use the cyanide ion. All right, and everybody take a second and tell me what my product of this reaction would be. All right, so first of all, bromine in water followed by sodium hydroxide produces what? An epoxide, right? So this is one of our methods for creating an epoxide. Okay. But if we're being good with our stereochemistry, I can't just use this straight line representation for my epoxide. Okay? Because this implies that all stereoisomers are represented. Right? All possible stereoisomers here would mean that these bonds could be, both wedges or both dashes or wedge and a dash. Whoops. Right, when you use that straight line bond, you're saying that all possible stereoisomers are represented. And one of these structures is just not feasible. Which one is that? If we go A, B, or C here, A, B, or C, which one's just not feasible at all? C, right? I can't have one bond pointing up on the ring, the other bond pointing down on the ring, and they're somehow attached to the same oxygen. So, because of that, we have to use our dashes and wedges. We have to show that this reaction is stereospecific. So we would get only the mixture of this, and it's an enantiomer, which is actually identical in this case because it's a meso compound, but yeah. So then when my nucleophile attacks, importantly, what do we call it again when we have our nucleophile attack and our leaving group leave all in the same step? SN2. And SN2 reactions are backside attacks. That nucleophile has to attack from the opposite direction of where my leaving group is. So that means that when I put my cyanide group, my nitrile group on my ring here, it's going to be pointed into the page and my alcohol group pointed out of the page. I guess if I was being really good, I'd have to say that there was a second step here to protonate that alcohol group, that alkoxide ion. All right, but importantly, we have a stereo-specific product here that we get. Okay, so with rings, I think it's kind of straightforward to see because it makes sense, right? One bond can't be pointed on one side of the ring and the other one on the opposite and get the same oxygen. All right, but this is what we would call, what we had called last semester. We already sort of saw reactions like this last semester. This is because this first step here is what's called a syn addition. And so this leads to these stereo-specific products. And again, it's kind of easy to see for a ring. It might not be so easy to see when we just have a regular old alkene. If we have a stereo-specific alkene, and we treat it and create an epoxide. So let's just use our other epoxide method, the MCPBA method. That's our other way of creating epoxides. That oxygen can only be attached on one side of that double bond. So either it's going to be placed on the very top or it's going to be placed on the very bottom. But my stereochemistry of this alkene is going to be preserved when my epoxide forms. Okay? So if I start out with my trans alkene, when my epoxide forms, I'm going to have one of those groups. I'll do my methyl group pointed forward. And just like in my alkene, that ethyl group was pointed in the opposite direction. So let me draw my epoxide. I guess I didn't finish that. And just like in my alkene, that ethyl group has to be pointed in the opposite direction, right? So if I start out with a trans alkene, I'm going to get a trans epoxide, meaning those two groups are pointed in opposite directions. Okay? And here I do have to say plus my enantiomer. All right, if I was going to be annoying on your homework, I would make you draw them both. It will accept either one of the enantiomers for your stereospecific product. But importantly, what's not going to be formed here, what you will not see any of, is when they were both on wedges or both on dashes. This here would be incorrect. Right? They started out pointing in different directions. My ethyl group was pointed in one direction. My methyl group was pointed in the other direction. That's going to be preserved when this epoxide forms. All right. And the importance of this is that it has consequences for now if we take this thing and react it with another nucleophile. All right, so first of all, let's first make sure that we get this down. I'm going to put down another epoxide here, or another alkene. We're again going to treat it with that MCPBA. want you to give me our stereospecific product that's going to form here. All right, and we're going to draw these, let me just say actually, we're going to draw these specifically in what's called a sawhorse conformation, where you keep that one bond, that epoxide bond, as a straight line and represent everything coming off of it as dashes or wedges. All right, we'll see why that is here in a second, but this is a specific kind of orientation, a specific way of looking at a molecule called a sawhorse orientation. All right, so in my mind, I'm going to imagine that this oxygen was placed right on top of this molecule. So that means that the methyl group on this side is pointed into the page. The methyl group on the other side is also pointed into the page. And that ethyl group is sticking out of the page on a wedged bond. If you drew this exact same conformation, but with your dashes and wedges flipped, that'd be fine. That'd be the plus EN portion. Either one of those would be accepted. Either enantiomer would be accepted. But importantly, regardless of how you drew it, your two methyl groups better be pointing in the same direction, because they're pointing in the same direction in our alkene. Okay? So now we're going to take this thing right here, and we're going to do a follow-up reaction with it. Okay, and again, I'm going to kind of do what I've been doing and keep my carbons of my epoxide colored. And we're going to treat it with HCl. All right, so first of all, real quick, do we have an acidic or a basic nucleophile here? Acidic, right? HCl. So does that mean it's going to want to attack the blue or the red carbon? We got some practice to do. All right, acidic's the weird one where they all always prefer the most accessible carbon, except for acidic nucleophiles. When there's a tertiary carbon, it wants that tertiary carbon. All right, so the chlorine is going to be added to that tertiary red carbon. Okay, if I'm being good, first there's a protonation step, so I guess I'll go ahead and I'll protonate my epoxide oxygen real quick, because I want to make a point here, which is that, again, that chlorine has to attack from the back side here. So from underneath this molecule. So we're going to use this sawhorse representation here, where we keep this bond in the plane of the page. All right. My oxygen is still attached to my blue carbon, my OH group. That's now pointed up. My chlorine has attacked that red carbon from the opposite side, so that is pointed down. On this blue carbon, there was a methyl group pointed into the page, so I have to include that methyl group. and on the red carbon there was a methyl group pointed into the page and an ethyl group pointed out of the page. Those dashes and wedges are going to stay the same, but now they got pushed up because that chlorine attacked from the back side. So I'm not going to change my dashes and wedges. I'm just going to orient them differently in space. Alright, so our consequence here, we have this stereospecific reaction. We started out with a specific stereochemistry of our alkene. That's going to lead to a specific stereochemistry of our product. If you started out with the enantiomer, you would have gotten, again, the same thing that I did here, but with your dashes and wedges flipped, and that's okay. All right, either one of those would be acceptable. Okay, so let's try to do another one from scratch here. I'll leave this up here as an example. So step one, we're first going to treat this, we're first going to create our epoxide. And then from there, we're going to treat it, this time with a basic nucleophile, an alkoxide ion. All right, and I want everybody to see if you can give me our stereospecific products here. Oh, I said I would leave that as an example. so when I draw my epoxide, I'm going to just start out with my triangle. I know I got that. The question is, how are all these groups oriented about this epoxide bond? Importantly, in my alkene, my ethyl group is pointed in the same direction as the propyl group and in the opposite direction as the methyl group, and I have to be consistent with that when I form my epoxide. So I'm going to imagine that this oxygen got put right on top there. So I have my ethyl group pointed into the page. I have my propyl group pointed into the page. And I have my methyl group sticking out at me. And again, if you did the exact reverse of this, if yours looks the exact same, but your dashes are wedges and your wedges are dashes, that's perfectly fine. That would be the plus EN portion here. Okay? So now I'm going to take this epoxide and I'm going to treat it with my basic nucleophile, the alkoxide ion. All right, if I color my carbons here blue and red, which one do basic nucleophiles prefer? Always the more accessible for basic. All right, so this thing's going to come along and attack from the opposite side here. So again, I'm going to start out with, let me see if I can shrink this down. My sawhorse model here, so I'm going to have my red and my blue carbons. The alcohol group from my epoxide is still on that red carbon. I still got my methyl group pointed in out at me. I still have that propyl group pointed into the page. And now I have my new alkoxide group, my new ether group here. All right, so your two functional groups you're going to keep in this sawhorse fashion, all on your straight lines. You're showing the stereochemistry of the other groups coming off of there. All right, and since that ethyl group on the blue carbon was on a dashed bond before, it's going to stay on a dashed bond. It's just going to be pointed in a different direction. Okay, I guess if I was good, I had to say 2, H3O+. We got to protonate that oxygen, but yes. All right, so this plus its enantiomer are my stereospecific products. All right, we can't use our we can't use our straight line bonds because that implies we got all possible conformations, the SS, the RR, the SR, and the RS. And it turns out that we only get 2 of those 4, right? So we have to show with our dashed and wedged bonds the stereospecificity of these reactions. This is obviously the biggest pain in the butt part of these types of reactions, right? Worst case scenario type of deal here, all right? But we got to remember, we talked about this last semester. There are certain reactions where we have this stereochemical consideration, and so we're going to start practicing that again this semester. You have 2 assignments for epoxide reactions. All right, the one that's due on Friday is just what the products are. And I say go ahead and ignore stereochemistry. Just use the straight line bonds. I want to make sure you know the difference between basic nucleophiles and acidic nucleophiles. All right, there's going to be another one, stereochemistry of epoxide reactions, that is going to specifically focus on this here, making sure that we can follow our stereospecific products of these reactions. Okay, cool. Break. Oh no, we're not done. We're just going to practice some alcohol reactions real quick. Rewind all the way back and make sure that we can do some of these. Sorry, I forgot we had time. All right. So starting with an alkene, we're going to do a whole bunch of crap to it. All right, so try to fill in this reaction wheel with all of these missing pieces here. Okay, this particular unit, you only got 2 chapters that we're combining into this exam, but there are a lot more reactions than what we had studied last time. Our reagent list has grown quite a bit. So keeping track of these reactions is going to be really important. Make sure to space out your studying. This is not really something that's going to sink into your brain with an 8-hour cram session the day before the exam. Space it out a little bit throughout the weekend to make sure that you can actually hold on to this information here, retain this information. All right, so let's start with the one that I think we all know just because we kind of beat it to death in this past week. MCPBA is going to create an epoxide. 1,2-epoxybutane based on what we learned today, right? We can name this thing now. All right, so then we have two more reactions of this alkene. One is using mercury acetate, and the other is using BH3. Both of these are going to convert that alkene into what functional group? An alcohol. And what's going to be the big difference between these two? Yeah, exactly. What we would call the regioselectivity, which carbon it's going to go on here, okay? So borane, BH3's claim to fame is to put that alcohol group on the less substituted carbon. So according to my coloring here, that would be that blue carbon. The mercury acetate is going to put it on the more substituted carbon. Okay. For this particular one, the other reagent that we could use that would do the exact same thing would be concentrated H2SO4. I'm sorry, no. Dilute H2SO4. H2SO4 in water. All right, the difference being this one is the one that you gotta watch out for shifts. We don't have to worry about it for this particular one, for this particular alkene, but that's the difference between those two reagents. Both prefer the more substituted carbon, but if you use the sulfuric acid, you gotta watch out for shifts. Okay, so now I'm gonna take this alcohol and I'm gonna treat it with this chromium-based reagent. And when you see chromium, you think oxidation. So this is a secondary alcohol. What do secondary alcohols get oxidized to? Carbonyls, but specifically ketones, right? So a secondary alcohol can only be oxidized to a ketone. It can't be oxidized any further. My primary alcohol, so now if we look down here, my primary alcohol, if I treat that with that same chromium reagent, what would I get? A carboxylic acid. That's because these chromium-based reagents we consider to be strong oxidizers. And a strong oxidizer would convert an alcohol all the way fully oxidized into a carboxylic acid. If I used PCC or DMP, these are also oxidizers, but they are considered to be weak oxidizers, which means that they would only oxidize that first step to an aldehyde, and then they stop. They're stuck there. Now I said PCC or DMP. On an exam, you would just see one or the other, right? They both do the same thing, but we need to recognize them both as weak oxidizers. Cool. Okay. So, the bottom line is we talked about, in the previous chapter, we talked about a bunch of reactions that created alcohols, a lot of which were reviewed from previous chapters. But then we also talked about things that we can do with alcohols. One of the big ones were these oxidation reactions, all right? The other thing that we learned how to do was to reverse an oxidation reaction, what's called a reduction reaction, right? So this reagent here would be what? So the key here is we would use one of these what are called hydrides. So either the sodium borohydride or the lithium aluminum hydride, either one of those will reduce a carbonyl group to an alcohol. All right, so yeah, we talked about a bunch of different reagents in this particular chapter. So again, flashcards are a really great way to study these various reactions, to get a good site recognition of what these reactions do. And again, make sure to space out your studying throughout the weekend. Don't save it all for one day, or it's going to be way too much information to try to cram in there. Cool.